in this lecture we'll answer on two questions. In the first question, we'll find out the length of line segment X, and in the second question, we will find out the value of the shaded area inside this quarter circle. So we'll start with the first question. In the drawing, we have a triangle ABC. This is triangle ABC. Angle ABC equals to 30 degrees. Angle ACB, this angle also equals to 30 degrees. And angle TAE, this angle equals to 60 degrees. And we also know that side line segment BD equals to 5 units, line segment CE equals to 4 units, and our mission is to find out the length of line segment DE that is equal to X. So first of all, we'll focus on triangle ABC. In triangle ABC, those two angles are equal to each other, they are both equal to 30 degrees. So we'll write it down that angle ABC, this angle, equals to this angle, this is actually angle ACB, and both angles are equal to 30 degrees. I'll repeat again. In triangle ABC, angle ABC equals to angle ACB, and both angles are equal to 30 degrees. Okay? And according to the rule that in front of equal angles in a triangle there are equal sides, so in front of this angle we have side AB, in front of this angle we have side AC, and according to the rule that I mentioned, AB must be equal to AC. Repeat again. According to the rule that in front of equal angles there are equal sides, in the triangle there are equal sides, side AB must be equal to side AC. So here those two sides are equal to each other. In the next step we'll define angle BAD, this angle is alpha, and we'll define angle EAC, this angle is beta. And we know that the sum of the angles in any triangle, and especially in triangle ABC, must be equal to 180 degrees. Okay? So the sum of the angles in triangle ABC equals to 180 degrees, that is to say, this angle equals to 30 degrees. This angle also equals to 30 degrees. This angle equals to alpha. This angle equals to 60 degrees, and this angle equals to beta. So in total, the sum of those angles must be equal to 180 degrees. Okay. This equation states that the sum of the angles in triangle ABC equals to 180 degrees. So here we have 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees, plus alpha plus beta, In total, they are equal to 180 degrees. So here we subtract 120 degrees from this equation and we get that alpha plus beta equals to 180 degrees minus 120 degrees. It is equal to 60 degrees. Okay. So we found out that alpha plus beta equals to 60 degrees. In the next step, we'll make two constructions. In the first construction, from point A, we'll draw a straight line in such a way that the angle that will be created between the straight line and side AC will be equal to alpha. So according to our construction, this angle equals to alpha, and the second construction that we will do is from point C, we will draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So actually this angle equals to 30 degrees according to our construction. Okay, in the next step we'll extend the straight line from C and the straight line from A until they intersect with each other. And we will define the intersection point between the two straight lines as point F. Okay, point F is the intersection point between the two straight lines. So actually we created here triangle AFC. In the next step we'll prove that triangle AFC is congruent to triangle ABD. Okay, triangle ABD is congruent to this triangle AFC. So why those two triangles congruent to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. So here, angle BAD, this angle, equals to this angle that is actually angle CAF, and both angles they are equal to alpha, therefore they are equal to each other. I'll repeat again, angle BAD equals to angle CAF, and both angles are equal to alpha, therefore they are equal to each other. In addition, those two sides are equal to each other according to what we have already proved. That is to say, side AB equals to side AC. According to what we have already proved, side AB equals to side AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So here, angle ABD, this angle, equals to this angle that is actually angle ACF, and they are both equal to 30 degrees, therefore they are equal to each other. Here I repeat again, angle BAD equals to angle ACF, and they are both equal to 30 degrees, therefore they are equal to each other. Okay, so we actually proved that triangle ABD this triangle congruent to triangle AFC, this triangle, according to angle side angle rule. I will explain what I mean. Here in triangle ABD we have those two angles, and the side that attached to those two angles, that is actually side AB. So in triangle ABD are corresponding congruent to those two angles, and the side that attached to those two angles, that is side AC in triangle AFC. Therefore those two triangles congruent to each other according to angle side angle rule. And from the fact that those two triangles congruent to each other, we conclude two things. The first thing is that side BD equals to side FC. BD equals to FC. So here side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Okay, those two triangles congruent to each other, therefore the corresponding sides, that is to say BD and FC, must be equal to each other. But according to what is given in the question, side BD equals to 5 units. Here we can write down that BD equals to 5 units according to what is given as the question, and from this equation 5 equals to BD equals to FC, we derive that FC is also equals to 5 units. Okay, here FC equals to 5 units. And the first thing that we will conclude from the fact that those two triangles congruent to each other is that side AD equals to side AF. Okay, side AD equals to side AF. Again, according to the same rule, the corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here AD equals to A according to our definition. So from this equation, A equals to AD equals to AF, we derive that side AF is also equals to A. Side AF also equals to A. Okay. In the next step, we will join points E and F together by a straight line. And we will prove that the green triangle, triangle ADE, this triangle is congruent to the orange triangle, triangle ADF, AEF. This orange triangle, triangle AEF. But before that, we already proved that alpha plus beta equals to 60 degrees. So here we have angle EAF also equals to 4 plus beta. That is to say, it is equals to 60 degrees according to what we have already found out. So why those two triangles can go into each other? So first of all, we just right now proved that those two sides are equal to each other. They're both equal to A, therefore they're equal to each other. Side AD equals to side AF equals to A. I'll repeat again. Side AD equals to side AF equals to A, therefore they're equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So you can write down that angle DAE, the green triangle, is equal to this angle that is actually angle EAF. And they are both equal to 60 degrees, therefore they are equal to each other. I repeat again. Angle DAE equals to angle EAF, and they are both equal to 60 degrees, therefore they are equal to each other. And finally, this side is a common side that belongs to both triangles, so this side equals to itself. AE equals to AE is a common side that belongs to both triangles. I'll repeat again. Side A equals to side AE is a common side that belongs to both triangles. And finally, so actually we found out that those two triangles, the green triangle is congruent to the orange triangle according to side rule. Triangle ADE, the green triangle, is congruent to the orange triangle, triangle AEF. According to side angle side rule. Triangle ADE congruent to triangle AEF according to side angle side rule. I will explain what I mean here. In the green triangle we have those two sides, and the angle that is located between those two sides are correspondingly congruent to those two sides, and the angle between those two sides in the orange triangle, therefore those two triangles congruent to each other according to side angle side rule. And from the fact that those two triangles congruent to each other, we will conclude that side DE in the green triangle is equal to side EF in the orange triangle. Here, repeat again, side DE equals to side EF. According to the same rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to X. So you can write here that side DE equals to X, and from this equation X equals to DE equals to EF, we will derive that side EF is also equals to X. Side EF equals to X. Here this side EF equals to X. In the next step, I will present to you the law of cosines and we will implement the law of cosines in this triangle, triangle EFC. So what is the law of cosines? I've already mentioned it a couple of times in the previous lectures. So the law of cosines is true in any triangle. So you can write here that in any triangle, so actually, if we have a triangle, this triangle ABC, that could be any triangle. This is triangle ABC. And we know that side AB of triangle ABC equals to A units in its length, side AC equals to B units in its length, and the angle between side AB and side AC is theta. And we also know that the length of side BC equals to C units in its length. Then, according to the law of cosines, the following equation is true: that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again, in this triangle ABC, that could be any triangle, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. So we'll actually implement the law of cosines in this triangle EFC. So I'll copy triangle EFC in this page, and we'll implement the law of cosines in this triangle EFC. Angle FCE, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. Side FC equals to 5 units in its length. Side EC equals to 4 units in its length. And side EF equals to X units in its length. That is the line segment that we are looking for. So this is triangle EFC that I copied from the original drawing. So we'll implement the law of cosines in triangle EFC. So according to the law of cosines, we get that here x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. I'll repeat again. In triangle EFC, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and cosine 60 degrees equals to 1 half, so we substitute cosine 60 degrees by 1 half. So in total this expression equals to 40 minus 40 times 1 half. So in conclusion, we found out that x squared equals to 16 plus 25. 16 plus 25 is 41, minus 40 over 2 is minus 20. So x squared equals to 41 over 2, that is to say 41 over 20 is 41 minus 20 equals to 21. So we found out that x squared equals to 21. Here we take out of this equation and we get that x equals to the positive square root of 21. And the reason that x equals to the positive square root of 21 is because of the fact that x is a length, it must be a positive number. So the answer to the question is that x equals to either the positive square root of 21, or in terms of numbers, it is equals to 4.58 units. Okay? So here x equals to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay? The line segment DE that is equal to x equals to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. We finished with the first question. In the next step I will present to you the second question. So in the drawing we have a quarter circle. Inside this quarter circle we have a circle and a semicircle that are tangent to each other at this point. And we also know that this circle is tangent to the quarter circle at this point. And our mission is to find out the value of the shaded area. Okay, so first of all, because of the fact that this is a quarter circle, this point must be the center of the quarter circle, and this angle must be equal to 90 degrees. So I write it down. So we define this point as point O, and point O is the center of the quarter circle. Okay, and this angle equals to 90 degrees. It is a right angle. It is true in any quarter circle. Always this point will be equal, this point will be the center of the quarter circle, and this angle will be equal to 90 degrees. Okay, so here we'll define this point as point A and this point as point B. So here we have tangent OA is tangent to this circle at point M. We define this point as point M. Point M is the point of tangency of tangent AO with this circle. We define the center of this circle as point P, and we will define the center of this circle as point Q. Point P is the center of this circle. Point M is the point on the circle itself. That is to say, PM is the radius of this circle that is equal to 2 units. And we also have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here, the radius OM, it is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also will be equal to 90 degrees. So we can implement rule number 1 in our drawing, because in our drawing we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AO with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius MP. So if AO is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. In the next step, from the center of this circle, that is to say from point P, we will draw perpendicular on QO. Okay. So here, this angle is equal to 90 degrees according to our construction, and this angle also will be equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and QO as L. L is the touching point of the perpendicular from point P and QO. Okay, so actually we have here quadrilateral LPOM. Inside quadrilateral LPOM, we have 1, 2, 3 right angles. So I write it down. Inside quadrilateral LPOM, we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees. Plus the size of the fourth angle, that is actually angle LPM, this angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, so here we will subtract 270 degrees from this equation, and we will get that the missing angle, angle LPM, equals to 360 degrees minus 270 degrees is 90 degrees. So we found out that the missing angle, angle LPM, equals to 90 degrees. It is a right angle. So this angle equals to 90 degrees. So actually we found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral LPOM as a rectangle. Again, quadrilateral LPOM is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle LPOM must be equal to each other. That is to say, here, side PM must be equal to side LO. PM equals to LO according to the rule that the opposite sides of a rectangle are equal to each other. That is to say, PM must be equal to LO in rectangle and POM. Okay. But we have already found out that PM equals to 2 units. It is the radius of the circle. So PM equals to 2 units. And from this equation, 2 equals to PM equals to LO. We will derive that LO also equals to 2 units. Okay, LO also equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that LP equals to OM. LP equals to OM, according to the same rule that the opposite sides of a rectangle are equal to each other. And if we define side LP as X, here side LP equals to X according to our definition. So from this equation, X equals to LP equals to OM, we will derive that OM is also equals to X. Okay, OM is also equals to X. Side OM equals to X. In the next step, we will focus at this point, that is actually the touching point between the circle and the quarter circle. Okay, so we'll define the touching point of the circle and the quarter circle as point K. Actually, the circle and the quarter circle have an internal length between them at point K. That is to say, they are touching each other internally at point K. And whenever we have an internal length between two circular shapes, then the straight line that joins their centers together must pass through point K, that is their touching point. So here, point O is the center of the quarter circle. Point P is the center of the circle. And OP is the straight line that connects their centers together. Here, line segment OP is the straight line that connects their centers together. And according to the rule that I mentioned, the straight line OP must pass through point K. That is to say, OPK is one straight line. Line segment OPK is one straight line. Repeat again, line segment OPK is one straight line because of the fact that the straight line that joins the centers must pass through point K. That is to say, OPK is one straight line. If OPK is one straight line, it means that OK is also a straight line. OK is a straight line. Okay, yeah. OK is a straight line. So here point O is the center of the quarter circle. Point P is the center, point O is the center of the quarter circle. Point K is the point of the quarter circle itself. That is to say, this is exactly the definition of a radius. OK is the radius of the quarter circle. So I can write down that OK is the radius of the quarter circle. Okay, okay is the radius of the quarter circle. So we will define the radius of the quarter circle as capital R. So we can write down that OK, that is the radius of the quarter circle, equals to capital R according to our definition. Point P is the center of the circle. Point K is the point on the circle itself. This is exactly the definition of a radius. That is to say, PK is the radius of this circle that is equal to 2 units according to what is given as the question. So I found out also that PK equals to 2 units. And what is the length of line segment OP? The length of line segment OP, it is very easy to see from the drawing that OP equals to OK minus PK. Again, OK minus PK equals to OP. So OP equals to OK minus PK. So OP equals to OK, but OK equals to the radius of the quarter circle, that is capital R, minus PK. PK equals to 2. So in conclusion, we found out that OP equals to capital R minus 2. Here, OP equals to capital R minus 2. Now we can, here, I forgot to write down that LO equals to 2 units. Here, we have already found out that LO equals to 2 units, so here I should have written that LO equals to 2 units, okay? So, in the next step, we will implement the Pythagoras theorem on the right triangle, triangle OPM. So I will copy the right triangle, triangle OPM in a new page, and we will implement the Pythagoras theorem on this triangle, triangle OPM. PM, side PM equals to 2 units, side OM equals to X units, and we've already found out that the hypotenuse OP equals to capital R minus 2. So this is the right triangle, triangle OPM that I copied from the original drawing. Now we will implement the Pythagoras theorem on this triangle, triangle OPM. So here, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse in the right triangle OPM is OP square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM square plus PM square. Okay, so here OP equals to capital R minus 2, therefore OP square equals to capital R minus 2 square, and it is equal to OM square. OM equals to X, so OM square is X square plus PM square. PM is 2, so PM square is 2 square, that is 4. So in conclusion, found out that according to the Pythagoras theorem and according to equation number 1, R minus 2 square equals to X square plus 4. Here we open the brackets on this side of equation number 1 and we get that according to equation number 1, R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2 is minus 4R, that is equal to X square plus 4. Here we have 4 on both sides of equation number 1, so 4 will get cancelled. What is left from equation number 1 after we cancelled 4? What is left is actually in this side of the equation we have R square minus 4R, that is equal to X square. So according to equation number 1, we found out that X square equals to R square minus 4R. In the next step, we'll focus at this point, that is the point of tendency of the semicircle with the circle, or the touching point of the semicircle with the circle. So we will define the touching point of the circle and the semicircle is point T. Actually, at point T, the circle and the semicircle have an external notch between them. That is to say, they are touching each other externally at point T. And whenever you have an external notch between two circular shapes, then the straight line that joins their centers together must pass through that touching point. In this case, point P is the center of the circle, point Q is the center of the semicircle, and the straight line that connects the centers of the circle and the semicircle is QP. And that QP, that straight line QP that connects their centers together, must pass through point T according to the rule that I mentioned. So here, the straight line QP must pass through point T, that is to say, line segment QTP is one straight line. Okay, line segment QTP is one straight line. You can also say that, in other words, that points Q, T, and P, they are all located on the same straight line. Okay, it is exactly like saying that QTP is one straight line. Okay, so here, point Q is the center of the semicircle. Point T is the point of the semicircle itself. That is to say, this is exactly the definition of a radius. So QT is the radius of the quarter circle, that is equal to 2 units according to what is given as the question. So here, point P is the center of the circle. Point T is the point of the circle itself. So this is exactly the definition of a radius. That is to say, PT is the radius of the circle, that is equal to 2 units according to what is given as the question. So what is the length of line segment, the straight line QP? Here QP will be equal to QT plus TP. I repeat again, the length of the straight line QP is actually QT plus TP. That is to say QP, the straight line QP equals to in its length to QT, that is 2 units, plus TP, that is also 2 units. So QT equals to 2 plus 2, that is 4. We found out that the straight line QP equals to 4 units in its length. Okay? In the next step, here we know that point Q is the center of the semicircle. Point B is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, line segment QB equals to 2 units. That is the radius of this semicircle according to what is given as the question. In the next step, we'll find out the length of line segment QL. What is the length of line segment QL? It is very easy to see from the drawing that the length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ minus LO. I'll repeat again. QL equals to BO minus BQ minus LO. So I write it down. QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LQ minus LO, that is equal to 2 units. I'll repeat again. The length of line segment of the, you can see also QL, the straight line QL equals to BO, that is the radius of the quarter circle, minus BQ, that is the radius of the semicircle, minus LO, that is equal to 2 units. So, in conclusion, we found out that the length of line segment QL equals to BO, that is the radius of the quarter circle, that is equal to capital R according to what is to our definition, minus BQ, that is equal to 2 units. This is the radius of the semicircle, minus BLO, that is equal to 2 units. So in conclusion, we found out that QL equals to capital R minus 2, that is to say, it is equal to capital R minus 2 is minus 4. So in conclusion, we found out that the length of line segment QL is capital R minus 4. Okay, here QL equals to capital R minus 4. Now we will implement the Pythagoras theorem on the right triangle, triangle QLP. So I'll copy triangle QLP in a new place, and we will implement the Pythagoras theorem on this triangle, triangle QLP. Okay. Side LP equals to X. We just found out that QL equals to capital R minus 4. And the hypotenuse QP, here, we found out that the hypotenuse QP equals to 4 units. This is 2 plus 2, that is 4 units. So we will implement the Pythagoras theorem. So here, this is triangle QLP that I copied from the original drawing. So we will implement the Pythagoras theorem on this triangle, triangle QLP. So by PT is the abbreviation for Pythagoras theorem. We get that according to the Pythagoras theorem, in the right triangle, QLP, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, the hypotenuse is QP, and the square of the hypotenuse is QP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QL squared plus LP squared. Okay, so according to the Pythagoras theorem and equation number 2, we get that here QP is 4, so QP squared is 4 squared, it is 16, and it is equal to QL squared. QL is capital R minus 4, so QL squared is capital R minus 4 squared plus LP squared. LP is x, so LP squared is x squared. So in conclusion, we found out that 16 equals to R minus 4 squared plus x squared according to equation number 2. Here we'll open the brackets on this side of equation number 2 and we get that 16 equals to R minus 4 squared equals to R squared plus 4 squared, it is 16, minus 2 times R times 4 is minus 8R plus x squared. Here we have 16 on both sides of equation number 2, so 16 will get cancelled. So what is left from equation number 2 after we cancel 16? In this side of the equation nothing is left, so it is 0. That is equal to, in the other side of the equation, we have, equation number 2, we have R squared minus 8R plus x squared. So here we will add 8R to this equation, equation number 2, and we get that according to equation number 2, R, 0 plus 8R is 8R equals to R squared. 8R minus 8R is 0 plus x squared. So here we subtract R squared from this equation, equation number 2, and we get that according to equation number 2, 8R minus R squared equals to x squared. So actually we have two different expressions for x squared. According to the first equation, equation number 1, we found out that x squared equals to R squared minus 4R, while according to equation number 2, we found out that x squared equals to 8R minus R squared. In the next step, we'll create equation number 3 that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So here, x squared according to equation number 1 is R squared minus 4R, and it must be equal to x squared according to equation number 2, that is actually 8R minus R squared. So we found out that according to equation number 3, R squared minus 4R equals to 8R minus R squared. Here we will add R squared to this equation, equation number 3, and we get that according to equation number 3, R squared plus R squared is 2R squared minus 4R, that is equal to 8R. Here we will add 4R to this equation, equation number 3, and we get that according to equation number 3, 2R squared, 4R minus 4R is 0, that is equal to 8R plus 4R is 12R. So here we will divide this equation, equation number 3 by 2, and we get that according to equation number 3, 2r squared minus 2 is r squared, that is equals to 12r over 2. 12r over 2 is 6r. So according to equation number 3, we found out that r squared equals to 6r. Here we subtract 6r from this equation, equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we take r as a common factor from this equation, equation number 3. So what is left from r squared after we took from it r as a common factor? What is left it is actually r. And what is left from minus 6r after we took from it r as a common factor? What is left it is actually 6. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r. The first solution for r is that r equals to 0. But because of the fact that r is the radius of this quarter circle, it must be a positive number. It can never be equal to 0. So we cancel this solution and we left only with the second solution, that r minus 6 equals to 0. Here we will add 6 to this equation and we get that r equals to 6 units. So we found out that the radius of the quarter circle is equal to 6 units. Now it is very easy to find out the area of the quarter circle. It will be equal to the radius of the circle, that is pi r squared, and r equals to 6 over 4. When we divide the area of the circle by 4, we will get exactly the area of this quarter circle. So what is the area, what is the value of the shaded area? The value, it is very easy to see from the drawing that the value of the shaded area, it is equal to the area of the quarter circle minus the area of the circle minus the area of this semicircle. I repeat again, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. It is very easy to see it from the drawing. Okay, so the value of the shaded area equals to the area of the quarter circle, and I have already mentioned that the area of the quarter circle equals to pi r squared over 4. That is the area of the circle over 4, and r equals to 6, of course. So it is pi r squared over 4, and the area of the circle equals to pi r squared, and r equals to 2. So r equals to 2, so therefore r squared is 2 squared. So the area of this circle is pi 2 squared. Minus the area of this semicircle, that is equal to the area of the circle over 2. The area of the circle is pi r squared, and the area of the semicircle is pi r squared over 2. And r equals to 2, so the area of the semicircle will be equal to pi 2 squared over 2. So in conclusion, we found out that the value of the shaded area equals to pi r squared over 4 minus pi 2 squared minus pi 2 squared over 2. We found out 2 minutes ago that the value of the capital R equals to 6 units. It is the radius of the quarter circle. So if R equals to 6, R squared is 36. In total, this expression equals to 36 pi over 4 minus pi 2 square. 2 square is 4, and 4 times pi is 4 pi. 4 pi is the area of the circle, minus pi 2 square over 2. 2 square is 4. 4 times pi is 4 pi, and 4 pi over 2 is 2 pi. So the area of the semicircle equals to 2 pi. And here 36 over 4 is 9. So in conclusion, this expression equals to 9 pi minus the area of the circle, that is 4 pi, minus the area of the semicircle, that is 2 pi. So here 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the shaded area the value of the shaded area, the value of this shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay, so we finished with the second question. In the next step I will summarize the lecture. We'll start with the first question, of course. So in the drawing we have triangle ABC. We know that angle ABC equals to 30 degrees, angle ACB also equals to 30 degrees, and angle DAE, this angle equals to 60 degrees. Line segment BD equals to 5 units in its length. Line segment CE equals to 4 units in its length. And our mission is to find out the length of side DE or line segment DE that is equal to X. So first of all we focused on the right triangle ABC. In the right triangle ABC, those two angles are equal to each other. They are both equal to 30 units, to 30 degrees. They are both equal to 30 degrees. So here in triangle ABC, angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. And according to the rule that in front of equal angles in the triangle there are equal sides, we get that here in front of side AC, in front of this angle that is equal to 30 degrees, we have side AC. In front of this angle that is also equals to 30 degrees, we have side AB, and according to the rule that I mentioned, AB must be equal to AC. Okay, so here AB equals to AC. Okay, and you also know that the sum of the angles in any triangle is equal to 180 degrees, and especially in triangle ABC, the sum of its angles must be equal to 180 degrees. We defined angle BAD as alpha, and angle angle EAC as beta, and according to the rule that the sum of the angles in any triangle equals to 180 degrees, therefore the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have in triangle ABC? We have this angle that is equal to 30 degrees, this angle also equals to 30 degrees, this angle equals to alpha, this angle equals to 60 degrees, and this angle equals to beta. So in total, the sum of those all angles must be equal to 180 degrees. So this equation states that the sum of the angles in triangle ABC must be equal to 180 degrees. So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 180 degrees. So here we found out that 120 degrees plus alpha plus beta equals to 180 degrees. We subtracted 120 degrees from this equation, and we found out that alpha plus beta equals to 60 degrees. Why? Because 180 degrees minus 120 degrees is 60 degrees. Then we did a construction. Here we did two constructions. From point A, we draw a straight line in such a way that the angle between the straight line and side AC of the triangle will be equal to alpha. So this angle equals to alpha according to our construction. We did also the second construction. From point C, we draw a straight line in such a way that the angle between side AC and the straight line will be equal to 30 degrees. I repeat again that this angle equals to 30 degrees according to our construction also. Okay, then we extended the two straight lines by straight lines until they intersect with each other at point F. And we proved that the new triangle AFC is congruent to this triangle, triangle ABD. Why those two triangles can go into each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. And finally, those two angles are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that this triangle, triangle ABD is congruent to this triangle, triangle AFC according to angle side angle rule. I will explain what I mean. Here, those two angles and the side that is attached to those two angles that is to say side AB in triangle ABD are corresponding congruent to those two angles, and the side that attached to those two angles that is side AC in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. Okay, so here we proved the triangle ABD is congruent to triangle AFC according to angle side angle rule. And from the fact that those two triangles can go into each other, we concluded two things. The first thing that we concluded is that side BD equals to side FC. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what is given us in the question, side BD equals to 5 units. So we can write down here that side BD equals to 5 units. And from this equation, 5 equals to BD equals to FC, we derive that side FC is also equals to 5 units. Here, side FC is also equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Here, side AD equals to side AF according to the sum rule that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we will derive that AF is also equals to A. Here, side AF is also equals to A. Then we joined points E and F together by a straight line, and we proved that the green triangle ADE is congruent to the orange triangle, triangle AEF. So why those two triangles can go into each other? First of all, we have already found out that alpha plus beta equals to 60 degrees, so this angle EAF equals to 60 degrees. So why the green triangle is congruent to the red triangle? First of all, we just right now found out that side AD equals to side AF, and they are equal to A, so they are equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, so side AE equals to itself. So we actually found out, can conclude from it that the green triangle ADE is congruent to the orange triangle AEF according to side angle side rule. Here, what I mean is that those two sides in the green triangle and the angle that is located between those two sides are corresponding congruent to those two sides and the angle that is located between those two sides in the orange triangle. Therefore, those two triangles congruent to each other according to side angle side rule. And from the fact that those two triangles congruent to each other, we will conclude that side DE equals to side EF. Okay, side DE equals to side EF according to the third rule that corresponding sides in congruent triangles are equal to each other. But according to what is given as the question, side DE equals to X. So we can write here that DE equals to X, and from this equation X equals to DE equals to EF, we will derive that side EF is also equals to F. Here, side EF is also equals to X. In the next step, I presented to you the law of cosines, and we implemented the law of cosines in this triangle EFC. The law of cosines is true in any triangle, so I'm going to write here that in any triangle. So what is the law of cosines? If we have this triangle ABC that could be any triangle, side AB equals to units in its length, side AC equals to B units in its length, side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times theta. I'll repeat again. According to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle EFC. Here side FC equals to 5 units in its length, side EC equals to 4 units in its length, and side EF equals to X units. And the angle ECF, this angle ECF equals to 30 degrees plus 30 degrees, that is 60 degrees. So we implemented the law of cosines in this triangle EFC. According to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. So here, x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40. And here we have also cosine 60 degrees. Cosine 60 degrees equals to 1/2, so we substitute the cosine 60 degrees by 1/2. So in conclusion, in total, this expression equals to minus 40 times 1/2. So in conclusion, we found out that x squared equals to 16 plus 25 minus 40 times 1/2. 16 plus 25, so here x squared equals to 16 plus 25 is 41, and minus 40 times minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. So x squared equals to 41 minus 20, that is 21. So we found out that x squared equals to 21. We took a root from this equation and found out that x equals to the positive square root of 21, and in terms of numbers, it is equal to 4.58 units. Here, the length of line segment DE that is equal to x must be, it is equal to the positive root of square root of 21. Why it is equal to the positive root of square root of 21? Because of the fact that x is a length, and the length must be a positive number. So x equals to either the positive square root of 21, or in terms of numbers, x that is equal to dE, it is equal to 4.58 units. So we finished with the first question. Then I presented to you the second question. So in the drawing we have a quarter circle. Inside this quarter circle we have a circle and the semicircle that are tangent to each other at point T. We also know that the circle is tangent to this quarter circle at point K. And our mission is to find out the value of the shaded area. So first of all, because of the fact that this is a quarter circle, here this point must be the center of the quarter circle. So point O is the center of the quarter circle, and this angle must be equal to 90 degrees. So this angle equals to 90 degrees. We define the point of tendency of tangent OA with this circle as point M. Point M is the point of tendency of tangent OA with this circle. And we also have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here, the radius OM, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. So we actually implemented this rule number 1 in our drawing. Here we have the radius PM that is drawn to the point of tendency, therefore tangent OA will be perpendicular to the radius MP according to rule number 1. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. So here point P is the center of the semicircle, is the center of the circle. From the center of this circle, we draw perpendicular on QO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And we defined the touching point of the perpendicular from point P and QO as L. L is the touching point of the perpendicular from point P and QO. Okay. So here actually we created quadrilateral LPOM. Inside quadrilateral LPOM we have 1, 2, 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees. So inside quadrilateral LPOM we have 3 angles that the sum of them is 270 degrees plus the size of the fourth angle that is actually LPM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtracted 270 degrees from this equation, and we found out that the missing angle LPM equals to 360 degrees minus 270 degrees, it is equal to 90 degrees. So this angle equals to 90 degrees. So we actually found out that inside quadrilateral LPOM we have 4 right angles. And then a quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral LPOM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle LPOM are equal to each other. That is to say, side PM equals to side LO. PM equals to LO. But we know that PM equals to 2 units. PM equals to 2 units. So from this equation 2 equals to PM equals to LO, we will derive that LO is also equal to 2 units. Here LO equals to 2 units. Likewise, according to the sum rule that the opposite sides of the rectangle are equal to each other, we get that LP equals to OM. LP equals to OM. So if we define side LP as X, LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we derive that OM is also equals to X. OM is also equals to X. Then we focus on point K. Point K is the touching point between the circle and the circle and the quarter circle. So here we have an internal notch between the circle and the quarter circle. That is to say, those two circular shapes are touching each other internally at point K. Point K is the touching point of the point of tendency of the circle with the quarter circle. And whenever you have an internal notch between two circular shapes, then the straight line that joins their centers together must pass through their touching point. In this case, it's point K. Repeat again. The straight line that joins the two circular shapes that have an internal notch between them must pass through their touching point. In this case, is point K. So here, the center of the quarter circle is point O. The center of the circle is point P. And the straight line that joins their centers together is the straight line OP. So this straight line OP, according to the rule that I mentioned, must pass through point K, that is their touching point. That is to say, OPK is one straight line. Okay? So here, OPK is one straight line. Or we also can say that points O, P, and K are all located on the same straight line. So if OPK is a straight line, then OK is also a straight line. OK is a straight line. But point O is the center of the quarter circle. Point K is the point of the quarter circle itself. That is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle. So we define the radius of the quarter circle as capital R. Therefore, OK, that is the radius of the quarter circle, equals to capital R according to our definition. Here, point P is the center of the circle. Point K is the point on the circle itself. That is to say, this is exactly the definition of a radius. That is to say, PK is the radius of this circle that is equal to 2 units according to what is given as the question. So we found out in conclusion that OK equals to R and PK equals to 2. Okay? And what is the length of line segment OP? From the drawing it is very easy to see that OP equals to OK minus PK. Again, OK minus PK equals to OP. I repeat again, OP equals to OK minus PK. So OP equals to OK, that is R, or capital R, minus PK, that is 2. So in conclusion, we found out that line segment OP equals to capital R minus 2. So here we can write down that OP equals to capital R minus 2. Then I copied the right triangle OPM in a new page and we implemented the Pythagoras theorem on this right triangle OPM. So this is the right triangle OPM that I copied from the original drawing. We just right now found out that hypotenuse OP equals to capital R minus 2. PM is the radius of the circle that is equal to 2 units, and OM equals to X. So according to the Pythagoras theorem, here PT is the abbreviation of Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The square of the hypotenuse is OP squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to OM squared plus PM squared. OP equals to capital R minus 2, so OP square is capital R minus 2 square, and it must be equal to OM square. OM is x, so OM square is x square, plus PM square. PM is 2, so PM square is 2 square, that is 4. So in conclusion, we found out that according to equation number 1 and according to the Pythagoras theorem, R minus 2 square equals to x square plus 4. Here we open the brackets on this side of equation number 1, and we found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R. And the other side of the equation we have x square plus 4. So here we have 4 on both sides of equation number 1, so 4 will get cancelled. What is left from equation number 1 after we cancel 4? What is left is that here we have x squared that is equal to R squared minus 4R. So according to equation number 1, we found out that x squared equals to R squared minus 4R. Okay, then we focus on this point T, that is the touching point of the circle and the semicircle. At this point, the circle and the semicircle have an external notch between them. That is to say, they are touching each other externally at point T. And whenever you have an external notch between two circular shapes, then the straight line that connects their centers together must pass through their touching point. So here, point P is the center of the circle, point Q is the center of the semicircle, and the straight line that connects their centers together is the straight line QP. And according to the rule that I mentioned, the straight line QP must pass through point T, that is their touching point. That is to say, QTP is one straight line. Okay, so here we arrive to the conclusion that QTP is one straight line, or we can also say that points Q, T, and P, they are all located on the same straight line. Okay, so point Q is the center of the semicircle, point T is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, QT is the radius of this semicircle that is equal to 2 units according to what is given as the question. Here, likewise, point P here is the center of the circle. Point T is the point of the circle itself. Therefore, PT is the radius of this semicircle that is equal to 2 units. So, what is the length of QP? QP equals to QT plus TP. Again, QP, the straight line QP equals to QT plus TP. Okay, so QP equals to QT, that is 2, plus TP, that is also 2. In conclusion, QP equals to 2 plus 2, that is 4. Here the straight line QP equals to 4 units. And here point Q is the center of the semicircle. Point B is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, QB is the radius of this semicircle that is equal to 2 units according to what is given as the question. So we found out that BQ equals to 2 units. So what is the length of line segment QL? It is very easy to see that the length of, from the drawing, that the length of line segment QL equals to BO, that is the radius of the quarter circle, minus BQ minus LO. Again, QL equals to BO minus BQ minus LO. And repeat again, QL equals to BO, that is the radius of the quarter circle, minus BQ minus LO. So BQL equals to BO, that is equal to capital R, it is the radius of the quarter circle, minus BQ, that is equal to 2, minus LO, that is also equals to 2. So in conclusion, found out that QL equals to capital R minus 2 minus 2. Capital R minus 2 minus 2 equals to capital R minus 4. So in conclusion, found out that QL equals to capital R minus 4. Now we can implement the Pythagoras theorem on the right triangle, triangle QLP. So I copied the right triangle QLP in a new page and we implemented the Pythagoras theorem on this triangle, triangle QLP. So this is the right triangle, triangle QLP that I copied from the original drawing. We have already found out that the hypotenuse QP equals to 4 units. We just right now found out that QL equals to capital R minus 4 and NP equals to X. So according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is QP, the square of the hypotenuse is QP squared. It must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to QL square plus LP square. So QP square equals to QL square plus LP square according to the Pythagoras theorem. QP is R minus QP, the hypotenuse QP is 4, so QP square is 4 squared, that is 16. That is equal to QL square. QL is capital R minus 4, so QL square equals to capital R minus 4 square plus LP square. LP is X, so LP square is X square. So in conclusion, we found out that 16 equals to R minus 4 square plus X square. We open the brackets on this side of equation number 2 and we found out that according to equation number 2, 16 equals to R minus 4 square. R minus 4 square equals to R square plus 4 square, that is 16, minus 2 times R times 4, that is minus 8R plus X square. So here we have 16 on both sides of equation number 2, so 16 will get cancelled. What is left from equation number 2 after we cancel 16? In this side of the equation nothing is left, so we have 0, that is equal to R square minus 8R plus X square. Here we added 8R to this equation, equation number 2, 0 plus 8R is 8R, that is equals to R square, 8R minus 8R is 0, plus X square. So in conclusion, found out that according to equation number 2, 8R equals to R square plus X square. Here we subtracted R square from this equation, equation number 2, and we found out that according to equation number 2, 8R minus R square equals to X square. So here we have two different expressions for X square. According to equation number 1, X square equals to R square minus 4R, while according to equation number 2, X square equals to 8R minus R square. Therefore, we created equation number 3 that states that X square according to equation number 1 must be equal to X square according to equation number 2. So here X square according to equation number 1 is R square minus 4R. And it must be equal to X square according to equation number 2, that is equal to 8R minus R square. So here we added R square to this equation, equation number 3, and found out that R square plus R square is 2R square minus 4R equals to 8R. R square minus R square is 0. So in conclusion, we found out that 2R square minus 4R equals to 8R. We added 4R to this equation, equation number 3. So here 2R square equals to 4R minus 4R is 0, and 8R plus 4R is 12R. So in conclusion, we found out that 2R square equals to 12R, according to equation number 3. Here we divided this equation, equation number 3 by 2, and we found out that 2R square over 2 is R square, and 12R over 2 is 6R. So in conclusion, we found out that R square equals to 6R, according to equation number 3. We subtracted 6R from this equation, equation number 3, and found out that R square minus 6R equals to 0. So here we took R as a common factor from this equation, equation number 3, and we found out here that, so R is a common factor. What is left from R square after we took from it R as a common factor? What is left, it is actually R. And what is left from minus 6R after we took from it R as a common factor? What is left, it is actually minus 6. So in conclusion, we found out that according to equation number 3, R times R minus 6 equals to 0. So here we will have two solutions that are possible for R. Either R equals to 0 or R minus 6 equals to 0. but r can never be equal to 0 because r is the length of the radius of the quarter circle. R is a length, it must be a positive number, it can never be equal to 0. So we cancel this solution and we left only with the second solution that r minus 6 equals to 0. Here we added 6 to this equation and found out that r equals to 6. So we actually found out that the radius of the quarter circle equals to 6 units. Now it is very easy to find out the area of the quarter circle. It will be equal to the area of the circle that is pi r square. And when we divide the area of the circle by 4, we get the area of the quarter circle that is pi r square over 4. And what is the value of the shaded area? The value of the shaded area, it is very easy to see from the drawing that the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. Repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the area of the quarter circle equals to pi r square over 4, and we know that r equals to 6. The area of the circle equals to pi r square, and r equals to 2, so it is pi 2 square. And the value of the area of the semicircle equals to pi r square over 2, and r equals to 2, so it is pi 2 square over 2. So here r equals to 6, so r squared is 6 squared, that is 36. So in total, this expression equals to 36 pi over 4. Minus the area of the circle, that is pi 2 square. 2 square is 4, so in total, this expression equals to minus 4r. And here, the area minus the area of the semicircle, that is pi 2 square over 2. 2 square is 4, and 4 over 2 is 2. So in total, this expression equals to minus 2 pi. So here, we found out that 36 over 4 pi minus 4 pi minus 2 pi equals to the area, to the value of the shaded area. 36 over 4 is 9, so in total this expression equals to 9 pi. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 units. I repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay, thank you very much.